All right, let's dive right into this explainer and demystify a totally critical yet totally unsung hero of global infrastructure, the industrial pipe flange. If you think about it, we're completely surrounded by these massive, sprawling networks of pipes. They carry water, steam, oil, gas, literally powering everything from our local grids to massive chemical refineries. But here's the catch. The pipes themselves are really only as strong as their connections. So today we're going to zoom in on those connections and decode the fascinating engineering language that keeps our modern world running safely. Think about it for a second. What does it actually take to safely contain explosive, high-temperature pressure when you've got toxic chemicals or superheated steam just coursing through a facility at high speeds? A ruptured joint isn't just a minor inconvenience, right? It's a catastrophic hazard. So, to understand how engineers guarantee safety under those extreme conditions, we have to learn how to read the secret language of pipelines. And honestly, the beautiful thing here is that this language isn't hidden away in some dusty filing cabinet somewhere. It's permanently stamped right onto the metal itself. If you look closely at the seemingly cryptic string of numbers and letters etched along the rim in the diagram, you'll see a sequence. It reads 3-inch, WN, ASME B16.5, 150 pounds, RF, A105, SCH 40, Heatno XXXX, and a little M logo. Now, to the untrained eye, sure, this looks like absolute gibberish. But to an engineer or pipe fitter, this is a highly detailed passport. It's like a structural nutrition label. It tells us exactly what this component can handle, exactly what it's made of, and exactly how it's meant to be used. To make sense of all this, here is our quick roadmap for the explainer. We'll start with the flange decoder ring, move into sizing and standard specs, then facing, material, and schedule. After that, we'll cover accountability and traceability, check out the physical flange anatomy, and wrap up with the price of precision. Okay, part 1, the flange decoder ring, where we start reading the secret language.
Moving right along to section 2, sizing and standard specs. Let's decode the core.
The very first number you're going to see in the sequence is 3-inch. This indicates the nominal size, which is often abbreviated as NPS, or nominal pipe size. Basically, this sets the baseline for the entire piping system. It is important to note, though, that nominal means it's a standardized designator. It's not necessarily the precise measurement of the pipe's outer diameter down to the absolute millimeter. Instead, think of it as the general category of pipe that this flange is designed to seamlessly mate up with. Next up in the sequence, we've got the marking WN, which specifies the flange type. WN simply stands for a weld neck flange. Now, there are quite a few types of flanges out there: slip-on, blind, threaded, you name it. But a weld neck, that's characterized by its long, tapered hub. This specific type is highly favored in really harsh environments, especially ones with extreme temperature fluctuations or super high pressure. Why? Because of how incredibly well it handles stress. We'll look closer at the actual physical shape of this later, but for now, just know that WN tells the installer exactly what type of connection they're dealing with. Now, this next part is absolutely crucial. ASME B16.5. This means the component adheres to a strict standard specification set by the American Society of Mechanical Engineers. You can think of B16.5 as the ultimate structural rulebook for pipe flanges and flanged fittings. Seeing the stamp is an absolute guarantee of universal engineering compatibility. It literally means a flange manufactured in Japan can perfectly mate with a flange made in Germany as long as they both carry this exact specification. It basically brings order to what would otherwise be total global industrial chaos.
Wrapping up this core sizing group is the 150 hashtag marking. This defines the pressure class rating, telling engineers exactly how much force the component can safely endure. Now, a really common misconception is that 150 pound means it can hold exactly 150 pounds per square inch of pressure. It's actually a bit more complex than that. It's a class rating that interacts with the temperature of the fluid inside. As temperatures go up, the allowable pressure actually goes down. But this specific class gives engineers the vital mathematical starting point they need for all their safety calculations.
Let's jump to section 3, facing, material, and schedule. This is all about fit and composition. So let's break down the next 3 codes in our table. First up, RF. That stands for raised face. This just means the area around the bore, where the gasket actually sits, is slightly raised above the bolting circle. It's a clever design because it concentrates the pressure onto a smaller gasket area, which creates a much stronger, tighter seal. Next, we see A105. This specifies the material grade.
In this case, a forged carbon steel that's exceptionally tough and pretty standard for high-temperature service. You literally have the chemical recipe stamped right onto the metal. Finally, SCH 40 dictates the pipe schedule, which corresponds to the pipe's wall thickness and bore size. Schedule 40 ensures the internal bore of the flange perfectly matches the internal bore of the pipe it's being welded to. That's super important for preventing any internal turbulence in the fluid flow. Moving on to Section 4, Accountability and Traceability. Think of this as the industrial barcode. Towards the end of that text string, you'll spot a marking like heat no XXXX. Now, to someone outside the industry, that might look like a typo or just some random serial number, but it is actually the most important barcode for material traceability on the whole component. The heat number traces this specific piece of metal back to the exact batch, or heat, of molten steel it was originally forged from. If a flange ever fails in the field, engineers can trace it right back and recall any other parts made from that exact same batch of steel. And right next to it, you've got the manufacturer's identifying logo, represented by an M here. This is their brand mark. It's basically the manufacturer putting their name and their reputation on the line, declaring they stand by the quality of this part.
All right, Section 5, Physical Flange Anatomy, what it actually is. Okay, so we're transitioning now from what the flange says about itself, all those textual specs we just decoded, to what it actually is in the physical world. Because the brilliant thing about a flange isn't just the material it's made of, it's the highly calculated 3D geometry designed specifically to distribute physical stress. Looking at the diagram's physical callouts, we can identify features 10 through 12. Number 10 points out the bolt holes, which are precisely arrayed along what's called the bolt circle diameter. This is exactly how the flange mechanically fastens to a matching one. Then, number 11 points to the central hub. Remember earlier when we decoded WN for weld neck? Well, this hub is that neck. It's a beautifully tapered cone. And finally, number 12 is the top edge, the weld end, where a butt weld connection physically and permanently joins this flange to the end of a pipe. This brilliantly illustrates the path of force and really shows why this shape is such a marvel of engineering. Imagine the process happening in real time. First, high-pressure fluid enters the pipe and hits that weld end connection at the top. Second, instead of that immense stress slamming into a hard, sharp corner, the energy and mechanical stress just gently travel down the hub's tapered neck. That smooth taper prevents stress concentration, which, by the way, is the #1 cause of metal fatigue and cracking. And finally, all that beautifully distributed stress safely transfers across the joint, tightly secured by massive bolts threaded through those bolt holes. The shape itself acts like a giant shock absorber for industrial pressure. And that brings us to our final section, the price of precision, and why these markings truly matter.
The reality here is that these aren't just arbitrary letters and numbers stamped onto metal for the sake of bureaucracy. A missing heat number isn't just a typo, it represents a fundamentally compromised system. Without absolute, complete traceability, without knowing the exact material grading like A105 carbon steel, or knowing that specific pressure class of 150, catastrophic failures become a very real, very terrifying threat. In a chemical plant or massive oil refinery, a flange failure doesn't just mean a tiny leak, it can mean a massive explosion. The precision of these markings is literally a matter of life and death. They ensure that every single link in the chain is exactly as strong as it needs to be.
To wrap up our deep dive, I want you to consider this thought. The precise markings on a flange act as its unique identity, telling you everything about its capabilities, origins, and structural integrity. It really is this meticulous identity system that allows pipefitters and engineers all over the globe, regardless of their language or geography, to collaborate safely. They rely on this exact system to build the massive, invisible infrastructure that powers our cities, fuels our transportation, and honestly, just sustains our daily lives. So I'm going to leave you with this final thought. Next time you happen to walk past an exposed industrial pipe, maybe in a boiler room, a factory, or even just some exposed city utility work, will you take a closer look? Will you be able to crack the code stamped right onto the metal? Hopefully, this explainer has given you the decodering you need to look at the highly engineered world around us with a whole new level of understanding and appreciation. Stay curious out there.